computer. Okay. So now, you see it now? Yep, okay.
Will there be error estimation questions on the final?
No error estimation.
Okay.
All right, so now we're set. So the exam goes all the way back to the beginning. And if you want to think in terms of, percentages, where the exam will focus, it's going to be pretty balanced. I mean, it goes all the way back to the beginning. Infinite series will probably make up less of a percentage. So if you really want to focus, yes, you're going to need to know all the tests. But power series, when it comes to the earlier material, power series will make a much higher percentage than infinite series. And then there will be plenty of material that covers the more recent stuff on parametric and polar curves. So going back to the beginning, we've got sequences. And if you think about it, essentially every test that we compute when we're studying series requires you to compute the limit of a sequence, right? And our main technique, right, is to replace the sequence with the associated function. Then you can use all the usual rules, L'Hopital's rule, squeeze theorem. Remember that you need to be able to deal with factorials, canceling factorials, and so on. And then we have the introduction to infinite series. Here, right, there's the S of n, that's the sequence of partial sums. Geometric series tests, repeating decimals. That's an application of geometric series tests. Telescoping series. We also learned the test for divergence here. .3 is the integral test. And there will be no error estimation, right? So P series shows up here. .4, that's the comparison test and the limit comparison test. 11.5 is alternating series test. Once again, no error estimation here. Um, 11.6, that's where we learn about absolute convergence, right? So now we need to be able to distinguish between absolute convergence versus conditional convergence. And in this section, we learn the ratio and the root tests. So that was the last of the tests. And then we move on to power series. So you need to be able to find the radius of convergence and the interval of convergence. And you should also, this is where we learned, and you need to know this, the behavior of the radius of convergence under substitution. So behavior of the radius of convergence under substitution. 11.9, that's representation of functions as power series. the key, I mean, the main thing that we use here, of course, is the geometric series combined with differentiation and integration. So we learned how to do that. So differentiation and integration of power series. So, oops, that should be an X to the end there. So if you have a power series, right, especially what we usually do is start with a geometric series, right, and then manipulate using differentiation, integration, substitution, and multiplying by, you know, a power of X, so X to the n. Those are the 4 standard ways to manipulate the geometric series, and that gives us the representation of lots and lots of other functions as power series. Now, not every single function can be manipulated, and so the more general approach is to use Taylor series. All right, so Taylor series gives us the sort of the most general way to find a power series representation. You should definitely know the standard or the common Maclaurin series. So, of course, geometric, and I'll just say it like this: 1 plus or minus, or 1 over 1 plus or minus x, exponential e to the x, sine and cosine, arctan. A natural log one is helpful, so like natural log of 1 plus or minus x. I don't always memorize the natural logs. Even the arctan I sometimes forget, and the reason is that I can very quickly derive them from the geometric series, right? So if you forget the power series for natural log of 1 plus x, within a few seconds you should be able to get it from the geometric series. Oh, and then the last one, I mean, don't stress about this one. It's just, I mean, it's a sort of messy formula, but the binomial series is also in there. Okay, so that's it for series. Any questions on this before I move on to the next chapter? No? Okay, so then the next chapter, we actually go back in the book. Oh, did I just write 10? Sorry, that shouldn't be 10:10. That should be 11:10 there. Right, and then we go back. 10.1 is where we introduced parametric curves. Uh, 10.2, that's where we do the calculus of parametric curves. So you should know how to compute derivatives, find area under a parametric curve. What else? Arc length, surface area. 10.3, that's polar, so polar curves. And then 10.4 is where we do the area of polar curves. So area and polar curves. Next chapter, 12.1, and that's where we introduce three-dimensional space. We learn the 3D distance formula and talk about spheres. .2 is the introduction of vectors. And so the operations that we learned that you can do with vectors, addition, Scalar multiplication. Length. We talked about the unit vectors, or what a unit vector is, and how to find the unit vector. So anytime if you have a non-zero vector, there is a unit vector that points in exactly the same direction, right? So you should know how to find that unit vector. 12.3 is dot product. And the key idea here, or the reason, is because there's a connection, between dot products and angles. Right, so then that equation right there gives us the connection between the angle between two vectors, right, and the lengths and the dot products. .4 is cross products. Oh, you know what? Oops, I skipped one thing. Sorry, I'm going to go back to 12.3 because I missed projections, right? Projections is also in there. Right, so you should know how to find the projection of the vector u onto the vector v. And then 12.4 is cross product. If you have two vectors, the cross product is a vector that's orthogonal to both of them. It obeys the right-hand rule, so that tells you the direction that it points in. And then in terms of length, we have this geometric interpretation that the length of u cross v is equal to the length of u times the length of v times the sine of the angle between them. And then you can interpret this as the area of the parallelogram determined by them, right? Anytime if you have two vectors, right, there is a corresponding parallelogram. And so the area of that parallelogram is exactly equal to the length of the cross product. .5 lines and planes. And there are lots and lots of different kinds of questions that can be asked regarding, connected to lines and planes. So you want to be very familiar with what the equation of a line does for you, or really the equations. I usually write parametric equations, and also what the equation of a plane does for you, right? And you should be familiar with all the different types of homework problems that were there. And I did some examples, but there are just so many different kinds of examples that you can do with lines and planes. So be familiar with that stuff. So then 13.1, that's parametrized curves. Sort of takes the two-dimensional parametric curves that we're looking at it and bumps it up a dimension. And so it sort of unifies the concepts, right? So now we can talk about parametrized curves in both R2 and in R3. 13.2, we get a bit of calculus. So we talk about the derivative of a parametrized curve, the antiderivative of a parametrized curve, tangent vectors, and tangent line. There's the unit tangent vector, that's capital T of T. Next
Can you
section.
say the tangent vector again, like the capital T of T formula?
Yeah, that is the unit tangent vector. So that is r prime of t divided by the length of r prime of t.
Okay, thanks.
Next, we have arc length and curvature. So the arc length, now we have a sort of unified formula to compute arc length, right? Little s is the arc length, and it's the integral from a to b. And what you want to notice is that the integrand is the length of the tangent vector, right? So this formula then holds in both R2 and in R3. And then curvature, there were a number of different formulas. The most computable, the most useful one is then this one right here, that the curvature is the length of the cross product, R prime cross R double prime, divided by the length of the derivative cubed. And then finally, we have sort of the physics applications of parametric curves. So position, you can view r of t as the position of a particle as it travels through space, in which case the derivative is interpreted as velocity and the second derivative as acceleration. And then the one application that we did was projectile motion. So that's it. That's the class in a nutshell. Any questions?
Wait, could you scroll up to like what's past 10.4?
Good, or farther?
A little bit down, like where 10.4 is at the top.
You want 10.4 on the top like that?
Yeah.
Other questions?
As far as the Taylor series section, do
Yeah.
we only need to know common Maclaurin series or coming up with the Taylor series for a certain function?
Oh no, definitely, yeah. So you need to be able to compute the Taylor series in general, and then if it turns out that you're looking at one of these familiar ones or need to deal with the familiar ones, it's useful to have those ones memorized. So absolutely, you need to be able to compute Taylor series as well.
Gotcha. Okay.
And that would be using the nth derivative formula, right?
Correct. Yeah, that's right. So yeah, so here, where'd it go? Yeah, you need to be able to find the coefficient. So that's the nth derivative evaluated a divided by n factorial. Definitely need to be able to do that. What else? So, all right, so we've got these practice problems. Obviously, we can't get through all of them. So are there any that you want to focus on? I mean, we got a half hour, so we can do as many or as few as you like.
I had a question on number 10. It's like jumping a bit forward, but
That's fine. So, yeah, and what is the question?
I have a graph drawn, but I'm not sure if it's the right graph.
Well,
Like, how would you go about doing this problem?
well, I would eliminate the parameter. And so what you notice, right? So what do we have? X equals cosine squared t and y equals sine, or not sine, cosine of the fourth to t. And then if you square the top one, what you get is that x squared equals y. All right, so the graph is a parabola, or maybe I should say it's really a portion of the parabola. So let's first draw the parabola. And then we want to recognize that x is cosine squared, which means that x has to stay between plus and minus 1. Same with y, cosine of the fourth has to stay between plus or minus 1. So the actual graph, right, is just that portion of the graph. All right. Other questions? All right, now's the time to speak up. Yep.
Can you go over 17?
17. Okay. So, okay, we're given acceleration, right? So a of t is 6t, e to the t 2. And so part A says find position, given that we know v of 0 and r of 0. Well, if we know a of t, then it'll take 2 antiderivatives to get back to r of t. So our first, we can go from acceleration to velocity by taking an antiderivative. And so that just means take the antiderivative of each one individually. So we'll get a 3t squared plus some constant c1, e to the t plus some constant, and 2t plus a constant. And now we know that v of 0 is equal to, where'd it go? 0, 1 minus 2. And so if I plug 0 in up here, that's going to allow me to figure out what C1, C2, and C3 are. So by plugging in 0, what we get, and here I'll write an in-between step here. This is V of 0, which is C1, 1 plus C2, and C3. So that tells us C1 equals 0, C2 equals 0, and C3 equals -2. So now in final form, V of t, 3t squared, e to the t, and 2t minus 2. Now we want to find r of t. So I need to take another antiderivative, and so we'll get t cubed plus some constant d1, e to the t plus some constant d2, and t squared minus 2t plus d3. And then we can use the fact that we know r of 0 to figure out who these constants are. So we have 1, 0, 0. That's r of 0. And that is d1 e to the t. Sorry, so no, e to the t is e to the 0 is 1. So that'll be a 1 plus d2 and d3. So that means d1 equals 1, d2 equals -1, and d3 equals 0. So r of t equals t cubed plus 1, e to the t minus 1, and t squared minus 2t. So that's part A. Any questions there?
What are you plugging in? So like if you look like where you're trying to, when you have D1 comma 1 plus D2, where are you getting that from?
Okay, so we know what R of 0 is. Well, R of 0 means plug 0 in for t in each of those spots.
Okay, so you get 0 plus D. Okay, that makes sense. And then when you go, then when you have the last step of when you solve for R of t,
Yep.
I'm
saying
you get like t cubed plus 1.
because D1 equals 1.
Oh, so then 1 plus D2 is 0.
1 plus D2 equals 0, so that tells me that D2 equals negative 1.
Oh, okay.
Right.
Okay, that makes sense.
Other questions?
Could
Okay.
you go over number 11?
Yeah, I'm going to do part B and then sure, then I'll do number 11.
Oh, okay. Sorry, my bad.
So let's see. Part B says now. So here's our parametrization. It describes some curve that is the path of some particle in space, right? So I have no idea what this curve looks like, right? So here's a generic picture of this curve in space. And the problem says, okay, this particle is traveling along the curve. So here it goes, it's traveling, and then let's say right here corresponds to t equals 1. At t equals 1, the particle slips off its track and it actually then goes in the direction of its tangent line. And so what we want to do is figure out now, where will it be? Where will that particle be 1 second later? So, well, let's figure it out where it was when t equals 1, right? When t equals 1, that point is going to be 2 comma e minus 1 comma negative 1. R prime of t, that is what, 3t squared e to the t squared minus 2. And so R prime of 1, that's going to be 3e negative 1. Oh, sorry, I should have said R prime of 1 right here. That's that vector. That's the tangent vector. So the equation of the line that this particle will now be following, right? The equation, the tangent line, parametric equations, is going to be 2 plus 3t, or x equals 2 plus 3t, y equals e minus 1 plus
Isn't R prime of t the z component 2t minus 2?
oh, did I screw something up here?
Because
2t, yes, thank you, right there. So if I plug in 1, oh, I get 0 there, don't I? Okay, thank you. So that R prime of 1 is actually 0 there. And then z equals negative 1 plus 0t. So that's the parametric equations for the tangent line. So now the question is, okay, so the particle slips off and it travels in the direction of the tangent line. Where will it be 1 second later? Well, let's plug t equals 1 into here and find out. Well, we're going to get 5. 2e minus 1 and -1. So that is the place that it will be 1 second after it leaves the curve. Questions? Okay, so let's look at number 11 now. So find the area enclosed by one loop of the curve r equals 3 sine 2 theta. So it completes one period at pi. So second period at 2 pi. And I want to mark some of the important points here. So this is pi over 4. This is pi over 2. 3 pi over 4. 5 pi over 4. 3 pi over 2. 7 pi over 4. Okay, so then I want to use this graph to sketch it in the XY plane. And so let's just notice here, so here I'll use some colors. As it goes from 0 to pi over 4, we start off with a radius of 0. At an angle of pi over 4, we're out to 1. And then we close up by the time we get to pi over 2. And then from pi over 2 to 3 pi over, pi over 4 to pi. Okay, so then we're over here. Then we're here. And so hopefully you can see by symmetry what this thing is going to do. Any questions on the sketch there? So then the area, to find the area, what I want to do is I'm going to, just find the area inside one leaf, and then, oh, that's all we want is one leaf or one loop. So the area is going to be 1/2 integral from 0 to pi over 2, 9 sine squared 2 theta d theta. We want to watch me integrate this?
Sure.
Okay, so I'm going to pull out the 9. So 9/2 integral 0 to pi over 2 sine squared 3 theta d theta. And then you want to remember to integrate.
Professor?
Yep.
Isn't it 2 theta?
Oh, yeah, thank you. Yep. There's an identity that tells us how to integrate sine squared, right? So this is going to be a 1 minus cosine 4 theta divided by 2 d theta. So that's going to be a 9/4 integral 0 to pi over 2. 1 minus cosine 4 theta d theta. And now we're ready to integrate. That'll be a theta minus 1/4 sine 4 theta from 0 to pi over 2. plug in the upper limit and we'll get pi over 2 minus, that'll be sine of 2 theta, so that's 0. And then when you plug 0 in, you get 0 all around. So in the end, looks like we get a 9 pi over 8. Any questions on that one?
So let's say, for example, the question was that we wanted all the area enclosed by the whole thing in one rotation. We couldn't just integrate the original function, right? We couldn't just throw that into an integral and that would give us the answer, right?
The entire area?
Yeah, like for all 4 petals in this case.
I mean, I guess I prefer to use symmetry and just multiply the result by 4.
Right. Okay.
But you can you just integrate from 0 to 2 pi.
And that'll give you the same answer. Or I mean, I guess not the same answer, but like that'll give you the right answer.
Yeah, it'd be times 4.
Okay.
Yeah, I mean, think about it. Your integrand, I mean, your antiderivative will be the same, but instead of plugging a pi over 2 in, you're gonna be plugging in a 2 pi. Right, which is just 4 times pi over 2. So you know, if you put a pi over 2 in there, it's exactly the same as if you multiplied the whole thing or multiplied my answer by 4.
Right. Okay.
Other questions?
Can you do 1e from the practice
One-
problems?
1e.
Yeah.
Yeah, now this one, you want to first use a rule of logs. Right, so I mean, when you look at this one, and this one just asks, is it convergent or divergent? When you look at this, there's really no test that jumps out and says, oh, this is the right test, right? I mean, it's not geometric. There's no partial fractions going on here. Comparison, limit comparison, I don't know. I mean, nothing jumps out. And so turns out this one's telescoping. Right, ratio and root test, they're not going to help you.
I forgot it was telescoping because you could like split up the natural logs into 2 different terms.
Yep, exactly. So now this tells us that S sub n is equal to natural log of 1 minus natural log of 2 plus natural log of 2 minus natural log of 3 plus ... plus natural log of n minus natural log of n plus 1. So you get cancellation all throughout the middle. And so you're left with natural log of 1, which is 0, minus natural log of n plus 1. And as n goes to infinity,
That goes to infinity as well.
that
Right?
goes to infinity, that's right.
And it diverges.
Yep, diverges. All right, so that approaches infinity, so diverges.
Thanks.
What else? And you know, that is one, if you are only thinking in terms of the tests, you're not going to get it, right? So you got to remember occasionally telescoping creeps in, right? So if it does not, if you have one that does not seem to fit with any of the tests, remember that there still is a telescoping series out there. What else? We got time for 1 or more 2 problems.
Can you
For
do
one?
number?
Go ahead, somebody.
Can you do number 13?
Okay, and then someone else said something.
I was just gonna ask for 1B. You don't have to solve it out, but would the test that you would use be the integral test?
Yep.
Okay.
Yep, that's probably all you got. And then who asked something about which problem?
I asked about 13.
13. Okay.
Just the setup would be good. I think I kind of understand the math. It's just like starting it that's hard.
Okay. Now here's the thing, and someone in the last class asked this. There's formulas. I think I mentioned this in lecture. In your book, there are formulas that tell you how to compute the distance between a plane and a point. And that's fine. If the question asks you how to compute the distance between a plane and a point, you're free to use that. But here's the thing. The questions can be rephrased or can be phrased in all kinds of different ways. And so I think it is much better, rather than memorize that formula, I think it's much better to just know, understand the process. So my recommendation would be this, right? We have the point, where'd it go? 411. And this is the plane 3x plus 2y plus z equals 1. My advice would be to find the closest point on the plane and then measure the distance between those 2 points. And the way to do that is to find the equation of the line that passes through 411 and hits the plane orthogonally. So the idea is to find the intersection of the line through 411 orthogonal to the plane and the plane. That's kind of a mouthful there. So find the intersection of the line through 411 orthogonal to the plane and the plane, right? So we're looking for the intersection of the line and the plane. So we're looking for that point right there. Does that help? Want to keep going?
Yeah, that makes sense. Yeah, that makes sense. Thank you.
Are the coefficients of the plane, that makes up a vector that's orthogonal to the plane, right?
Yes, the normal vector is 3, 2, 1.
Okay.
And that's going to be the direction vector for your line. Right? Because
in this case, would the normal vector kind of like not lie on the plane because it doesn't really look that orthogonal? It would like kind of point out to the side.
who? Wait, who points off to the side?
The normal vector for the plane.
No, I mean, no. The normal vector is directly orthogonal to the plane. This is, this is just a schematic of the plane. I don't know exactly how it slants. I just kind of drew a plane there. So don't take that as accurate in terms of how the plane looks.
Is it always going to be like that the normal vector is the direction vector when you find the distance between a point and a plane?
Well, if you want to find the line that's orthogonal, then absolutely.
Okay, sounds good. Thanks.
Other questions? We got a couple more minutes.
We do 12. I could skip part A, just B and C probably. There's time.
Okay. So for part B, so what do we got? U is -101. V is 211. We want an equation of a plane, which means I need a normal vector. This plane contains both of these vectors, which means the normal vector is going to be the cross product of these vectors, which is -1, 3, and -1. So there's our normal vector. And when I say the position vectors, That means the vectors that emanate from the origin, which means that this plane contains the origin. So now we can just write down the equation of the plane, right? If you know a point that it passes through and a normal vector, you're done, right? Minus x plus 3y minus z equals 0. All right, now we want the parametric equations of the line that meets the plane orthogonally. If it's going to meet the plane orthogonally, then its direction vector has to match, has to at least be parallel to the normal vector. So we might as well choose the direction vector equal to the normal vector. So the parametric equations will be x equals 4 plus 3t, y equals 1 plus 2t, z equals 1 plus t. Oh, sorry, I looked at the wrong one. Sorry. I was looking at the wrong vector. Normal vector here is -1, 3, -1. So that should be minus t plus 3t and minus t.
How did you know that the plane contained the origin?
Oh, sorry, you guys. I think did I screw this up? What problem am I looking at? I'm looking at the wrong problem, aren't I? Sorry, I mixed 13 and 14. Let me start over on the second half of this. I wrote the problem. I wrote the numbers down for the plane in 13. So this line passes through. Where'd it go? I'm doing problem 12. I'm doing 12, right?
Yeah, 12C.
So okay, so it passes through. Right. Sorry, 1, 2, 3, and the direction vector. Oh. Is -1, 3, -1. So x equals 1 minus t, y equals 2 plus 3t, and z equals 3 minus t. There we go. I'm sorry, somebody had a question there at the end. What was that?
I guess this is more for B. When you're, so I get how you find the normal vector for the plane by doing the cross product. How do you find like what it equals? You said plane equal, or plane contains the origin like 0, 0, 0. So
Yeah.
you said negative x plus 3y minus z equals 0. Like how do you
Yeah.
know it's equal to 0?
It's always equal to 0.
Oh, okay.
Whenever you're setting up the equation of plane, you always set it equal to 0. So normally, if it would have passed through a different point, like let's say it passed through the point 1, 5, 7, then I would have written negative x minus 1 plus 3 times y minus 5 minus z minus 7, but it's always equal to 0.
Oh, okay, yeah.
What I did here, I was subtracting 0, 0, 0, so it was a little easier, but you always set it equal to 0 on the other side.
Gotcha.
What controls the signs for that second equation you wrote for 1, 5, 7? Why is there a negative out front of the x minus 1 and the z, but a positive in front of the 3 times y minus 5?
Oh. -1, positive 3, -1.
Oh, okay, so those are the coefficients, and then the point is what? Okay.
Correct. The coefficients come from the normal vector.
Okay.
Right. Okay, I got another class joining here, so I'm going to wrap things up. I will see you Friday.
Thank you.
Thank you.